Hello, I'm Richard Gunton, and I'm going to talk to you about p-values, what they are, what they mean, and how we should use them, and then how this connects to the challenge of learning about the world. Now, we never actually see the causal processes or the mechanisms or laws of nature behind how the world works. What we can see are data, so particular observations. So here we are wondering how the world works, wondering about processes that might be kind of beneath our feet, as it were, which are generating the experiences that we get when we observe data. We can't just see how the world works. What instead we do is we use data. Now, in everyday life, we do this intuitively. We observe what comes into our experience and we form beliefs. And there are ways of studying how people do this and why we sometimes get them wrong. Cognitive psychology, for example, looks at this. In data science, we use a formal framework based on mathematics and the concept of probability. We might still form false beliefs and get things wrong, but at least we have a framework which we can refer to and hopefully try and improve. So, on to p-values. Supposing I have a machine, I'm the manager of a factory, and I have a machine generating widgets, and every so often one comes out faulty. I have to decide, do we have a problem here? Do we have to stop the machine and get it calibrated? Well, let's suppose that for financial reasons, I know that if it's no more than 1 in 100 that come out faulty, then that's okay. So I'm going to have a sort of default hypothesis that says 1 in 100 or fewer are coming out faulty. And I can take that as a probability. And in fact, with very simple maths, I can work out the chance of getting different numbers of faulty widgets if that's the case. So let's suppose I'm going to observe 100 coming out of the machine. The most likely number to come out faulty, of course, is 1. It's round about a bit less than 0.4. And simple maths can help us find that. We're almost as likely to get 0 faulty widgets in a batch. We're much less likely to get 2, and progressively less likely still to get 3, 4, 5, and so on. Now, let's suppose that I observe this machine and 100 widgets come out and 4 of them are faulty. What do I do? This seems suspicious. It seems to make the hypothesis suspicious. Well, I can easily find the probability of getting 4, but I'm going to take this as a special case of 4 or more faulty widgets, and of course in any order, because I'm questioning whether we're in the territory where we need to get the machine stopped and calibrated. So we've got 4 or more. I can find the probability of that. And it turns out to be about 0.02, about 2%. And that is a p-value. That's the p-value for that default hypothesis. And it says that the data are really rather unlikely if that hypothesis were true. So, is that what I want? Well, it does seem to be suspicious. It seems to make that default hypothesis rather implausible. We'll come back to that thought in a moment. But this approach can be extended and used in lots of similar ways. So maybe I could be waiting instead for how much time it takes until something goes wrong with a machine or some fault comes along. And I can find the probability distribution, which this time will be continuous, for amounts of time that it might take under some null assumptions, some basic default. So maybe I find that after 3 minutes, that's when the first fault develops. And I can say, what's the probability of getting 3 or more minutes when I'm waiting? And that probability over here will be a p-value in a similar way. We can do this for other cases too. We can do it for comparing means, take the average of something and see if it's suspicious with respect to a default hypothesis. We can do it for correlations, for regression slopes, and so on. But what does it actually mean? Well, it's saying that the data would be this much likely or unlikely according to the default hypothesis. Now, of course, that's not really what we wanted to know. We want to know, should I believe this hypothesis? How likely is it to be true? And the only way to get that conclusion is to go beyond, to really abandon this p-value approach and use a Bayesian framework, where you have to feed in a prior idea of how likely it is and then update it with some observations to get a posterior. But in this p-value approach, what's actually happening, I think, is connected to simple philosophy, because supposing I had a hypothesis that said it's impossible to get faulty widgets from this machine, then conversely, if I did get a faulty widget, that would make the hypothesis impossible. And that's what philosophers call the modus tollens argument. So in this case, we don't deal with impossibility usually, but it's as if we say, if the hypothesis makes the data almost impossible, then it seems as though these data make the hypothesis almost impossible. But as I say, that's an intuition, that's not actually rigorous reasoning. So we have to use p-values carefully, ethically in fact. We have to say carefully why we came up with that particular default assumption, hypothesis, how many data we collected to try and test it, what alternatives we consider. We must quote the actual observation we got. It seems obvious, but people often get so excited about p-values that they don't, and so on.